Energy is inherently a part of everything we do in our lives, but one of the least understood things.
By giving people agency around their energy, around power, you are giving them power.
This is a moment in time with technological advancement that allows for humans to take advantage of the free aspect of energy.
I can see a future where there is limitless and free energy. And that's a pretty beautiful world to live in.
All right, welcome back, John. Today we're going to be diving a lot into really how does energy consumption work, and how does the bigger system work of energy, but also there's been a lot of discussion around battery storage, BESS as it's known in the industry, but like there's been so much discussion around the opportunity that's there, but also a lot of confusion around the history of BESS too, which will be really exciting to get into just because there's a little bit of chemistry there. And I know we've touched on it on a few other episodes too, but like this will be kind of our opportunity to go a little bit more in depth.
So what I'm going to show here, and I'm going to pull up a little visual aid, is a graph produced by the Lawrence Livermore Labs. And
which, those of you who don't know, Lawrence Livermore National Laboratory is like one of the best in the world at what they do.
Yes, indeed. And they've been doing these for these type of Gantt charts for several years. And so what we've got on the screen right now is California's total energy consumption in 2022. And so there's a lot of lines and colors and jazz on here, but we'll break it down. So starting on the left, we have all of the sources of energy. So solar, nuclear, hydrogen, or hydro power, rather, natural gas, coal, petroleum, etc. And then as we move from left to right, it starts to get into the uses. So the first big box that you see there is electricity generation. So that's supplied by natural gas, by solar, by nuclear, etc. And just a little teeny bit by things like biomass and geothermal. And then that electricity generation and all the rest of the power sources flow toward the end uses, which are residential, commercial, industrial, and transportation. And then on the far right, we've got our rejected energy and our energy services, those two ideas that I just mentioned. So one thing that you can notice right away is on the far right side, the rejected energy box is about 2/3 of the total. You might look at this and go, why are we rejecting so much? Why are we wasting so much of the energy that we produce? It takes a lot of work to get these resources in play, to generate the electricity, to transport it, to use it, to produce the products that use the electricity in useful ways. Why are we wasting so much of it? And you can see from kind of the lighter gray bar going from the pink boxes, a lot of that is coming from transportation. Why is that coming from transportation? Because it's using fossil fuels. And like I alluded to with you turn on your car and it goes, that noise, that heat, that vibration, that is all rejected energy. None of that is going to useful services. Although, I mean, some people find the noise useful. I don't know. I don't know why. Anybody that drives an EV I don't think is going to miss the roar and the rumble. But essentially, they're very inefficient. Fossil fuel technologies tend to waste a lot of the energy because you're combusting something. You're burning something, and that produces soot. It produces different kind of molecular compounds. In the form of like carbon monoxide and other carbon dioxide, other gases that we produce a lot of and aren't necessarily great to do. But so
I'm just more fascinated by the fact that a lot of this chunk is just transportation, period.
Yes.
Like I would have thought kind of the biggest energy consumers would have been industrial, commercial, and residential, because transportation is a piece, but like I didn't expect it to be as large as it is. Do you think that's our infrastructure transportation, that we kind of like rely on motor vehicles as our mode of transportation versus public transportation? Is it the cleanliness of that form of transportation? Where do you
Um,
think that really lands?
well, if you look at the pink transportation box, you've got the big fat light gray, and then the little tiny dark
Mm-hmm.
gray. That dark gray is all of the energy that is actually used to transport everything in California.
Mm-hmm.
The rest of it is all just wasted. So, um, in California, primarily our primary source of greenhouse gas emissions is from the transportation sector, and it's not even close. And
Mm-hmm.
this is kind of getting to some of that issue, but um, yeah, we have a lot of people in California. We have a lot of cars in California, and we do a lot of shipping. From coast to coast, and we're
Agriculture industry and
the Santa Cruz area, this the Central Valley is the breadbasket of the country.
mm-hmm.
The what do they call it? The lettuce bowl of the
Yeah.
country. And so there's a ton of transportation, and essentially all of it is petroleum based. And because of that, it's hugely inefficient, and that's what this is showing.
Yeah.
So only a small fraction of all of the oil and gasoline that we use to transport goods and services in this country is actually going toward transporting those goods and services. It could be hugely more efficient. So that's why electric vehicles and electrification is so crucial. And you can see this pattern in other places in this graph. It's a little more subtle than that, that big obvious chunk going to rejected energy from transportation. But if you
Mm-hmm.
track more closely, and all this is available online um, for people to go in and after this and really look at it closely. But most of the big chunks of rejected energy you can link directly back to either petroleum or natural gas.
Mm-hmm.
And so that's because, like I alluded to, they're combustion based, and that inherently is a pretty inefficient form of generating energy.
Mm-hmm.
So as we're kind of on the cusp of this AI uh, revolution, whatever you want to call it, explosion, where we're having to massively increase our energy supplies to feed the data centers and all that stuff. Um, it should make you start thinking, well, how can we use what we already have more efficiently? How can we
Mm-hmm.
start to shrink that rejected energy box and expand that energy services box? Electrification is the answer. And so
Mm-hmm.
the two big pieces there are EVs and batteries, battery energy storage. And
Mm-hmm.
so, but today I think, let's focus on battery energy storage because that plays into not only EVs, because EVs, what are they? They're batteries on wheels.
Mm-hmm.
But energy storage can come into play on basically most parts of this graph. So behind the meter, front of the meter, utility scale, residential scale, distributed, concentrated, you name it. You can put batteries in there.
Well,
So,
it's one of the things we've also hit a couple times of the thought that like we generate enough power, we just don't store it to then distribute it. And I think that that's kind of that missing puzzle piece. I think for a lot of this is the idea of the stored energy. I think to kind of the technological advancement side of things, it's like, yeah, our technology is there, but the infrastructure is not there to make a meaningful transition in transportation of goods from petroleum to something else, because battery doesn't necessarily work as well for like these big ships, but there's alternative ways to do it. And then how do we integrate this into more of the manufacturing side? I think again, it's like application of all these energy solutions. And I think on the best side, I think that that has the most upside and opportunity at the moment, because there really is so much energy that we generate. I mean, even this chart shows that how much energy is actually generated. If we could utilize more of that, reduce that rejected energy, whether that be from petroleum or otherwise, like, and utilize it, best seems the way to store that energy. Um, so where did kind of this battery energy storage start to come about? Because I know there's been a little bit of a history of like, yes, battery fires. I remember when Teslas first came out, people were like, well, when a light's on fire, they're going to keep burning. So, oh my gosh, danger. And then also you had Moss Landing last year. Where does all of this fit in terms of battery energy storage? Because I think we're also up against this weird thing of like, you have a little bit of pushback from the safety side of things.
Yeah,
And I know we've hit on it before, but it's like, it doesn't really apply anymore.
exactly. Yes, and yeah. So it's as you mentioned, it's they've gotten some bad press because of some pretty high visibility failures. Um, but okay, so batteries have been around for a long time. You know, there's some very ancient technologies that may or may not be batteries, but they kind of look like batteries, like the Baghdad batteries, if you've ever gone down that rabbit hole. But mostly when people think of batteries, at least up until kind of the rise of EVs, it was lead acid batteries, or the little like AA, AAA batteries, and those are based on a particular type of chemistry. And it's usually alluded to in the name, like lead acid. It's got lead and it's got acid. Um, and those were, they for what they are, they're very reliable. They're pretty easy to make, and they're fairly cheap. And so, that was kind of our gold standard for
Mhm.
at least automotive batteries. But then as we've learned to harness the power of lithium, we've been able to get greater and greater energy densities out of our battery technology, and that's really what the key is. You think about like future, like sci-fi futures with flying cars and hoverboards and all of that technology uh, would rely on extremely energy dense energy storage.
Mm,
So, because you want it to be light and you want it to have high output, and those two things they're tough to achieve. Because the more energy you cram into a little space, kind of the more dangerous it is, because
mhm.
you have more energy in a little bit of space. um, it's like having a line of gunpowder versus a stick of dynamite.
Mhm.
They're very, very different kind of reactions, very different outcomes.
Well, and you're also battling that, that weight and performance side of things. Because I remember I've known like an electric yacht company for a long time, and in that industry, what's so interesting is when you think about like the resistance of a boat against water,
Hmm.
water's incredibly hard to get through,
Oh yeah,
and at a certain point, if you add more battery to get more range, you're not going to get more range because you're putting more weight, which is then pushing again. And so the breakthrough that was needed on that was better battery efficiency
exactly.
and more power in a more condensed area, just magnified because it's on the water versus land.
Yeah, and exactly the same for airplanes, for electric
Hmm.
airplanes. You put in more bigger, heavier battery, you need more power to take off, and so yes,
Hmm.
so that's why all those hover cars and hoverboards are, they need a very, very energy dense battery.
Hmm.
So we've been making progress toward that, and the first few iterations of lithium ion batteries were not that great, maybe even worse than the lead acid, but it's the kind of thing where it has promise, it has the potential for evolution, whereas the lead acid had already, the technology curve had already kind of plateaued. Um, and so some of the first big energy storage installations. So like, kind of utility scale, large batteries used for flattening and controlling grid demand and things like that. Those were based off of a particular type of chemistry that's known as NMC, nickel, manganese, and cobalt.
Hmm.
And um, it's a pretty high energy density, maybe a little too high for what it is, but that it so they was good at doing things that required that level of energy density, and also quick discharge and quick recharge,
Hmm.
but it came with some pretty huge drawbacks that produced these high visibility failures that we mentioned earlier. So in particular, once NMC battery catches on fire, it's really hard to put out. You have to basically starve it of oxygen. You can't use water because it burns so hot, the water will split apart into oxygen and hydrogen, and both of those things will combust and drive the fire further. So when one of these things catches on fire, you really just kind of gotta wait until it burns itself out, which is obviously not ideal, especially if you've put it in some kind of building that's going to catch on fire. At which, I'm kind of dropping hints. We'll talk about the Moss Landing battery fire later. That's exactly what happened.
Mm-hmm.
So after these kind of, some of these high visibility failures had happened, and there was starting to be a public backlash against the safety of the NMC battery technology. Another technology that had been kind of waiting in the wings, but waiting for its moment because it was slightly lower energy density, slightly slower discharge, recharge, but much, much safer. It's LFP, lithium, iron, which is Fe
F.
in chemistry, and phosphate. And if you just kind of think about those two types of chemistries, just kind of what's conveyed in the name, lithium, iron, and phosphate, all of those things are biologically compatible, and in some
Mm-hmm.
cases, absolutely essential for life. Whereas nickel, manganese, and cobalt, not really something you want to like take a big bite of,
Mm-hmm.
not something
Mm-hmm.
you want to put on your plants as fertilizer. Can be
Yeah.
fairly toxic. And so besides their energy properties, just like the atoms themselves, the elements themselves are fundamentally different, and the LFP is fundamentally safer. And
Mm-hmm.
so there's there's that kind of toxicity element, and then there's also the slightly lower energy density and the way that the molecules and the atoms bond together in the LFP chemistry, and the way that they store and release power. It does not. They basically can't go into that thermal runaway process where they start burning so hot that they split apart water.
Mm-hmm.
So that is kind of just off the board for that for the LFP.
Wow.
Much safer on a fundamental level, both in terms of combustion and toxicity. So
Wow. So are we
yeah.
basically looking at call it a triangle, if you will, of kind of the energy capacity, the recharge and discharge and safety, and you can't have all three, but you get two out of the three. And where are you on that? Is that kind of the
At least,
choices you get?
yeah, at least where we are right now. Maybe someday
We'll
somebody will
find a
make,
miracle one that'll just
yeah,
hit all
you
three.
just grab a handful of sand and throw it in a box, and you can power your hoverboard. But
You know what's funny? They actually do have that. They have sand batteries. They're very. I'm serious, and
oh no, the
we
thermal, right?
yeah. They
Yeah,
basically underground and then heat and then basically just cycle it through.
yeah.
It's a pretty thoughtful solution depending on your geography. It's like that would actually kind of make sense.
Yeah, well, that's the thing about energy is it can neither be created nor destroyed, at least in our
Hmm.
current understanding of things.
Yeah.
So mostly what it does is it changes form from one to another. And
Hmm.
there are all kinds of ways in which it does that. And so it's really up to us to figure out how can we tap into that transformation, that transmogrification from one form to another. And we've been getting better and better at it, as we have more understanding of, energy itself, and, different material science, and all that kind of stuff. So all this is to say that the lithium ion batteries of today are much safer than the ones from just 5-10 years ago.
Hmm.
And so I think now it's time to talk about Moss Landing. So
Yes. Yeah. So, for those of you that don't know, Moss Landing is kind of between Monterey and Santa Cruz, kind of right in this beautiful Monterey Bay sanctuary, otters. Like, it's known as one of the most diverse areas in I'd argue the world, but hey, who are
no,
locals?
it's a
But yeah,
very unique
it's
place.
yeah,
Yeah.
and I remember growing up, and you just see these, you'd see these stacks in the distance, and every once in a while you drive through, and I was always blown away by the scale of it. Just and then you learn that it's also like a reserve power station, which I didn't know that for a long time. But yeah, that was just context around Moss Landing in general. But John, take it away, because yeah, obviously they had quite the event at the end of last year that made some headlines across the nation.
Yeah, so those smokestacks, they were for most of my life growing up in Santa Cruz. They were it was the PG&E Moss Landing power plant, which was a natural
Mhm.
gas power plant, and those tall smokestacks were to lift up the smoke from combusting the natural gas above the thermal inversion that causes the fog in the Bay Area, or in the Monterey Bay Area. Sorry,
Mhm.
different Bay Areas, right next
Yeah.
to each other though. And so that power plant was basically converted over the last several years, maybe the last decade, into a big battery energy storage facility. And so a company called Vistra was working with PG&E on a multi-phase battery installation. And these were large, like it was like 2% of California's total energy storage capacity, um, uh, like 200 megawatts, something like that. Or gigawatts, I don't know. It was large, about 2% of California's total energy capacity, energy storage capacity. And these were NMC batteries, so high capacity, high discharge, high danger,
Hmm.
especially the way that they did them. So, yeah, earlier this year, back in February, there was an accident there. One of the battery systems, one of the larger ones, caught on fire, and it started to burn, and it burned the building that it was in, and it caused a huge pillar of smoke to rise up. It could be seen for miles and miles around, and of course, it's right on a sensitive marine area. Got the Monterey
Naturally
Bay right
drew a
there.
lot of attention.
Naturally drew a lot of attention. Moss Landing itself is not that populated, but it's between two, quite populated areas. Um, and so they issued an evacuation. They had all the first responders come, and they kind of just had to stand around and go, well, let's make sure it doesn't go any further, because, like I said, you can't just spray water on this stuff. It will combust the water and make the fire
Mhm.
worse. So they just had to let it burn out, which you know made the pillar of smoke that was in the air last quite a long time. And then they did some testing afterward in the nearby areas, the beaches and the riverbeds and the ocean and stuff like that, and they found uh, really high levels of nickel, manganese, and cobalt nanoparticles, which I studied environmental nanoparticle toxicity for my PhD. So I was like, oh boy, this is not, this is not good, because most people aren't really kind of clued into the fact that um, nanoparticles behave very fundamentally differently, and they can have some really weird properties. And if you don't know what they are through intensive study, you really can't predict what the effects on the environment are going to be. So
Mhm.
not great to have all that stuff out there, especially for potentially toxic metals like cobalt and nickel and manganese. And so it naturally and justifiably drew some public backlash. And
Mhm.
there's been a lot of talk, both at the county level and at the state level, about what do we do to make these technologies safer?
Mhm.
Should we put a pause on things while we study it? Should we like get rid of stuff that we've already installed? All kinds of stuff. And so I wanted to like dive in and understand, how did this happen? What went on there? And it turns out there were some pretty big flaws with that installation that were directly responsible for how bad of an accident it was. Which, just to put it into context, like something like 12 Mile Island took millions and millions of dollars and over a decade to like clean up. So this was like a week, and nobody got hurt. The evacuations were temporary. It shut down part of the Highway 1 for a little bit, but they reopened
Mhm.
it. Overall, very limited impact on like economic stuff and also public health and safety. The environmental stuff, we'll see. But
Mhm.
overall, the severity of this accident was not that great, even though
Hmm.
this was like the worst battery fire in human history.
Hmm.
So
Yeah.
I think that's important to keep in perspective too. It's like even though this was the worst, accident in battery energy storage history, it still wasn't that bad comparatively.
Yeah.
It wasn't an oil spill. It was no Exxon Valdez. It was no, yeah, it was no
Hmm.
Chernobyl. So but even still, there are plenty of ways that we could have prevented this from happening, and plenty of ways in which we are preventing it from happening in the future. So the first one
Hmm.
that is obviously the NMC battery chemistry. Now it's kind of out of date. It's basically all or most of the things that are coming online now are the LFP, which is a much safer one. And so, right off the board, we can take that off the table in terms of like if we were to do another, if we were to replace what happened at Moss Landing with stuff now, how can we make it safer? So that's step one. Step two is that it was put in an old building. So that power plant had been there for a long time, decades, and so the battery itself was housed in an old like hall kind of building that was not meant to house a battery. And in fact,
Right.
modern
But was it designed though to kind of like just kind of have a roof over it, like so that way you have not as much. I mean, not that the South Bay area or Monterey Bay area changes that much temperature wise, throughout the year, but is it for like more temperature stability for operations?
no, no, it
Yeah,
was
just
I think it was just like we have this building, let's put a battery in it.
got it.
Um, which is not what the current modern safety standards are for batteries of basically any size. You want to put them outside. You want to put them
Yep.
in their own unit. You want to give them a safe space in case they catch fire. You want to put them on a concrete pad so they don't spread that fire around. And usually you put them in like a big, hefty metal container so that
Hmm.
nothing catches on fire around them. Um, so that was the second flaw was
Hmm.
they put it in an old building. And then the third, which is probably the biggest component to all of this, is that they had a leaky fire suppression system in that building that had caused three other battery fires at that site. So it was basically water pipes, on the ceiling that were meant to, activate sprinklers,
Hmm.
which really, I mean, it shouldn't have been in place in the first place, as we've discussed.
Right.
Water is not an effective way to put out an NMC lithium battery fire. Um, but they were just drip, drip, drip water on the batteries because they were leaky, and eventually that caused a short, which caused some thermal runaway, which caused the battery to catch fire. So it wasn't even the battery itself that was the trigger
Hmm.
for the failure. It was these water pipes that had been leaking on it for God knows how long, and it caused three other fires at the same facility. So like that is that's to me that's like the big one. We could have easily avoided this whole thing if they just had taken out that fire suppression system anyway, because obviously it didn't work.
Is that ever communicated, by the way? Like in terms, like just for the public? Because I think when you have more of an understanding of that, even a riskier battery technology, it wasn't the battery technology that actually caused the issue.
No,
Um,
no.
I find that interesting. Like I wouldn't have thought that. I would have thought, oh, the battery failed and therefore something
Just like
happened.
they're
Is
all
that ever
bound to fail. No, it was not bound to fail, even though it was an older technology, even though it was put in a building that it shouldn't have been in. It was because they were
Hmm.
dripping water on it constantly. Like, it's
Got it.
just not, that's not something you should be doing to your battery. I mean, you think about like dripping water in your laptop all day long, like that's not, you wouldn't want to do that. That would
Well,
cause a
I think
failure.
that speaks to also just I mean, I like that now our safety standards are set to, hey, outside, concrete pad, like it's not that hard to run the energy from outside to the building. Like that
Yeah.
risk is way less than putting it, out of sight, out of mind in a room somewhere. I think that really helped on the infrastructure side, and arguably like as bad as the event is. Don't get me wrong, as bad as the event is, it also does bring like a certain level of awareness around battery technology that we didn't have before. Yes, with a
Hmm.
little bit of backlash, but it puts in the forefront of discussion. But then also, I think it shows that, like, as awesome as energy is and as incredible as it is something we have to be aware of from a safety perspective. Like, if you think about how much energy is actually flowing through these systems, it's kind of crazy to think that humans even set this up. Like, it's a lot
Yeah.
of power.
Yeah.
And I think that's the other adjustment is, I think, even the ease of which batteries. Like, I remember when I was a kid, those nickel metal hydride batteries came out, and it was like I could charge my Walkman by, putting my batteries on a charger rather than those little Duracells where you check the. I think as we've adopted electricity and electrification into our lives, it's become this like, oh, it's so safe. Nothing bad can happen until it does. And I think
Yeah.
sometimes that reminder does help us to kind of rethink, like, hey, we actually are, this needs to be a safe technology going forward. And I think we have started to achieve that. But this is one of those very public things where the public was like, oh, let's not forget that these things can go sideways. But it is our responsibility to kind of do the best we can, because it can happen in any type of industry.
Yeah, and any form of energy storage. Like
Mhm.
like I mentioned, the more energy you compress into a space, the greater the potential hazard is going to be.
Mhm.
And
Mhm.
that's just a natural consequence of compressing energy into a small space. It has nothing to do with the particular technology, although, obviously some are safer, some are more resilient, some are longer lasting. But, the fundamental principle is there that we have to respect it. We have to be careful, and nothing comes for free, but some things are cheaper than others, and the LFP batteries are, overall have a much lower societal cost than NMC batteries, but also from coal, from fossil, from natural
Mhm.
gas, from petroleum, because they don't produce greenhouse gas emissions that cause climate change, and they are much much more efficient. So getting back to what we started this conversation with, um, if we had more batteries,
Mhm.
regardless of what kind, that rejected energy box would shrink a lot, and the energy services box would expand a lot, which would mean that we were getting more bang for our buck,
Mhm.
as an economy, as a society, which we don't have unlimited resources, and so it's if we want to do we want to do the best with what we have, at least in my
Well, we're
mind.
also at this point of society where there is a huge need for more energy, like more than we've ever needed, I
Yeah,
think, in
and
human
more and
history.
more.
So when you have that much of a need, of course you're going to have one side that you need to, like, generate more, yes. But also, how do you maximize what you've already generated? I think is one of those things where not a lot of the focus, I feel like, has been on purely like generate more energy, which there needs to be that. But like, yeah, I mean, the rejected energy chart, like, it shows that there's a lot of energy that we could utilize in a better way, and BESS is kind of the way to do it. I
Yeah.
think it's a way to put into an energy strategy. Like, um, I think maybe some businesses are really at like a spot right now where they're going, oh, do I generate more energy? Do I just pay for the energy? Do I store the energy? What's the best energy strategy? And I'm like, well, in this situation, I mean, you want stored energy anyway, like, no matter what. It's like, to me, it meets whatever demand you need. It's kind of like that necessity that goes in there. And then however that stored energy gets powered, that can kind of fluctuate a little bit depending on your needs.
Yeah, and we have the technology now where a business that's really committed to the new energy future can basically kind of opt out from the system as it exists right now. If
Hmm.
you have a discrete facility, you've got like a building, a set of buildings, you put those all on a microgrid, you put solar on, you put batteries on, you don't have to talk to PG&E anymore. I mean, you,
Hmm.
you do, but you don't have to pay them a bunch of money, especially because they keep raising their rates every year, and
Hmm.
those rates might go up faster than ever before with all of the new energy demand from the data centers, especially in
Yeah, I mean, it's
Silicon
it's
Valley.
naturally a pressure on the system that comes from supply and demand. And I think it's, if you think about a lot of companies that they look to secure their supply chain, well, this is part of that supply chain. Energy is a necessity in the supply chain for whatever the product is, whether it's software, hardware, whatever. It's a piece of that, and more stability, more efficiency, more sustainability in that area, and sustainability in the sense of like, sure, planet, but also just business. It's a huge piece that I think is
Yeah.
just really important.
And once you've made the investments in those solar panels and those batteries, you have those materials now as part
Hmm.
of your inventory, and you can recycle them, you can reuse them, you can
Hmm.
repurpose them. So it's not just like it's like the difference between renting and owning, right? It's right now we're basically renting. We pay PG&E or whoever our power company is, just month after month, for a service that they provide. But we could buy too. Like businesses can buy to own, and once they own those solar panels, once they own those batteries, that's their material, that's their lithium, that's their silicon. It's and they can recycle it, and they can put it back into play. They can get some value out of it after they've got their use out of it.
But when you're looking through it as like as an investment mindset of like as a business, we're gonna commit some capital, some capex to build out our energy category of our company. Is this like 5, 20, 30, 40 years? Like what's the horizon? Because I think given the context of Moss Landing, I think probably some of the fear might be like, well, what if some problem comes up with lithium down the road? That kind of thing of like, we didn't know that technology would have that, necessarily bad angle at
Yeah,
that time. Like,
we kind of did, but it
yeah,
was it was it was worth the
worth the
trade-off.
risk. Yeah.
And
And
yeah, because we
so
didn't
is there
have
that
the
fear of
newer,
like,
safer one.
if we invest in 5 years, that chessboard looks totally different in energy? Is that the point we're in? Or is it like you're investing now for like 20 years and it's going to continue to pay dividends? Is that, because I think the timing of that investment into your energy strategy, some people might think it's 2 years, some people might think it's 5, some might think it's 10. What do you think it is?
Well, so there's always a cost of not investing, right?
Hmm.
So if the longer you wait, that you're losing some savings. You're losing some
Hmm.
revenue if you wait. But of course, you don't just want to rush into to everything, right? So
Hmm.
what you're alluding to, and um, knowing being familiar with this technology space, with this industry, we know that this set of technologies, solar, microgrids, LFP batteries, they're all safe enough and reliable enough that like really there's not a lot of drawbacks. I mean, the only drawback is the price, which has been continuing to come down. But even that, if that comes at a trade-off. Like, is the price going to come down in the next 2 to 5 years enough that it offsets any potential savings that you're going to get? That's kind of a question that you would have to say, talk to us here at Mint and figure out on a case by case basis for your
Hmm.
for your particular company. But really, I think it's the sooner you can get into that space, the better, because you get off of the just paying utility bills every month, and you
Hmm.
start being able to control your own energy demand and supply,
Hmm.
which gives you um, greater flexibility, greater potentiality as a business, and it also gives you greater reliability and resiliency, especially if you're a business that provides an essential service, that people need all the time. If you're a hospital, you need batteries. I mean, they already have batteries and generators in place, but this is even better, than a
Hmm.
diesel generator that you have to buy the fuel for, and then release clouds of smoke into the air and all that kind of
Hmm.
stuff. So um, there are lots of benefits from adopting as soon as you can, because
Hmm.
the benefits will continue to accrue year after year. And you know,
These batteries also last a very long time. Like, I
yeah,
think
at
that's
least
the
at
other
least
thought. Like,
at least 20 years. And that's kind of like,
yeah.
it's like 20 years for like the warranty. There will be some degradation over that time, but there's already starting to be some technology, some techniques to like revamp and revitalize batteries, which is pretty cool. There's some really cool research coming out of China on all this stuff because they've just been going full steam ahead on renewables and batteries, and yeah, they've been figuring out ways to basically recycle batteries while they're in place. So as the you know the capacity starts to degrade, they have some little tricks, and yeah, you
I have
can
a
get
friend
that
of
back.
mine in Europe who also has been looking into that concept of like, can you rejuvenate a battery? And
Yeah,
basically theirs is like when a cell, theirs is much more on the small scale at the moment, like literally just for the person or your house or an appliance or something like that. But like when a cell dies, be able to replace the cell like
yep,
immediately and just like replace it and fully recycle it. And I think like that is going to be kind of the future where you're laying the foundation and then you're replacing cells and pieces and whatever you need along the way.
yeah, yeah, absolutely. Which is much more economical and much more sustainable. So
100%. And I think it becomes more accessible too,
yeah,
because then the longevity can be, if you want to upgrade your system at a certain point to whatever the new technology is, cool. If you have the capital to do it, awesome. But you won't necessarily need to because you could extend the life of your already existing battery even longer than you made a good investment on. I think
yeah,
it's just a good idea.
it creates a whole secondary market as well. Which is it's a whole other thing.
Yep, 100%. Well, John, this has been fantastic. I'm looking forward to kind of going a little bit deeper on this best stuff, especially as it progresses, because I know it's changing very rapidly. It's an exciting space to be in right now. So, I love that you're up on it, and especially from the chemistry side, like I find that so fascinating. So maybe we'll get into some of the battery chemistries that are coming down the pipe too, just so that way people are aware of where the world's going too.
Yeah, absolutely. Sorry, my cat's impatient.
All good. Well, John,
All right.
thank you for another great episode.
Yeah, thank you, Steve.
Energy is inherently a part of everything we do in our lives, but one of the least understood things.
By giving people agency around their energy, around power, you are giving them power.
This is a moment in time with technological advancement that allows for humans to take advantage of the free aspect of energy.
I can see a future where there is limitless and free energy. And that's a pretty beautiful world to live in.